Someone to Hey, good afternoon to everyone. Today's weather is quite hot. So we have 3 replacement class to make for the semester. So I was planning to do 15, 29, and 6. 11 this Monday. Monday 11 to 1. Once I book the venue, I'll let you know. Okay. Yeah, replacement class. 15, 29, and 6. Yeah. What do you mean? 15 is next week. One more week. Why? You go through tonight. Oh, 1 week on. Is it just you on? Hmm? Yes. Others okay.
It's not things.
Huh? Think what?
I'm currently you got one year. Next week I'll be able to
What time? What's that? What day? 15. Also 15. Please check.
So
15.
there's statistics, right?
Mhm.
Replacement class 1 to 3 on 15, 32nd, 29, and 6 May.
Oh, but mine is 11 to 1. So okay, right? 11 to 1. Yeah. Because I also have no time. After your class, I still got another replacement. 1 to 3 also. So I also know not many. No. So maybe who is that? Ivan, maybe you watch recording or not? I excuse you. Okay, you watch recording for that day because you also have limited time to do. Okay, yeah, I excuse you. You can be absent. Right. Okay, once I know the venue, I'll let you know. I will put out the notice. So it's 11 to 1 now. Okay. Another thing is I already put out last week tutorial and assignment. So the point of the tutorial, I don't put solution first because I want you to do it first, try it on your own. And you can even send your answer for me to check if you want, okay, or ask me anything about it. And then I will post the solution later. And if you found assignment is very hard, right? That's the point. Okay, that's the point. Because I want you to talk to your friend, ask your friend, discuss with your friend, not just do it on your own. Okay. So Hanwei, Ethan, no, is the Ethan Hanwei. Ethan asked me what's research about. So the way I teach the courses here is very research oriented. So for example, I teach you how to bring a broom, but I will ask you to sweep the floor. So you need to figure out, once you know how to take a broom, you need to know how to use it. Not by just yourself, you can discuss with your friend and so on. Okay, I saw that like Jing Seng, they already start doing the assignment, right? So if you have any problem, maybe you can ask him. Have you finished the assignment? Not yet, huh? Okay. Yeah, maybe. Huh? Sorry? Too difficult. Too difficult. Actually, I put a hint in the I put a hint in the Moodle, right? Did everyone see or not? I put stuff on purpose that I don't simply upload file for you to read. Okay, so let me show you. Show you. Okay. So I put out this book here. Right. So I have one question from this book. Okay. Basically, it's about natural numbers, but today we will look at Peano axiom, but the Peano axiom here is using set. So it's like combination of the set and the natural number. So I want to see whether you can understand how to manipulate set notion. Okay. And please don't just copy answer from there. You have to write in your own word. Okay, understand it and then write in your own. Okay, if you don't understand certain statement, then you can ask me. Okay, or ask your friend. Does it make sense? No? Yeah, if you don't understand this line, why this line is true, why is this following this line, then you can ask me or ask your friend. Get help. Okay? Yeah, but don't copy it, but write in your own word. Okay, so far any question or not? Regarding assessments, regarding last week lecture, any problem you made when you do revision? Okay, please submit your assignment on time. Okay, don't make a habit that drag and procrastinate this habit. Any question before we start? Where did we stop last week? So last week we did two main things. So first is propositional logic. Okay, what statement is true, how to decide a statement is true or false, how to prove method, and then please do the tutorial. You exercise how to do different type of proofs. Okay, actually your class has an advantage. You know what's your class advantage or not? Yeah, one of them is active in class. You listen very well. Okay, but let off exercise. Please do exercise more. Then you will be good already. You will be in very good shape, actually. Does it make sense? Yeah, please do exercises. Okay. You guys have a very good advantage than the other class. Okay. So we have propositional logic last week, and then we built set theory. Okay, talk about elements, and then we group them together as a set. So this week we're gonna build number system. Okay, we will start building number system from natural numbers. So to you, what is natural numbers? Any idea? What kind of structure you have? So this lecture, right, share a bit of flavor with abstract algebra. Okay, so how to build natural numbers? What's natural number to you? Okay, one by one say. I think you saw natural number for how many years already? How many years? How old are you? 20, maybe 20 years already. Right. So what's 20? 20 is a natural number. Okay, so what can natural number do? Would represent what? Natural thing, sure. You want to count, and then what can you do with natural numbers? Tell me. What can you do with natural numbers? If I give you a bunch of natural numbers, what can you do with them? Yes, you can add them, and then sure, minus. Minus is what? Is the inverse of plus. Okay. What else? Multiply. Okay. And then sure, divide maybe. Yeah. Okay. And between each natural numbers is the difference is what? Huh? One. I mean successively. Okay, it's one, right? 1 to 2, 2 to 3, 3 to 4. The smallest gap is 1. Okay. So we want to characterize this structure. Okay, and then we call it natural numbers. So the first axiom is we will start with 1. Okay, there's 1 inside the set. Okay, now you should forget what is natural number, and then we try to build from scratch. How to build 1, 2, 3, 4, 5, 6 until 100, until billion, so on. Okay, so first we just start with one thing, which is 1. Okay, and then next we want to say what are the things are equal inside this set. How to tell whether 2 is, does 2 equal to 4, does 2 equal to 3, or how to decide. Okay, how to decide two things are equal. So first, we require that everything is equal to itself. Okay, so this one should remind you about equivalence relation. Okay, when we want to talk about equalities, right, we always want equivalence relation. So first, you have to equal to yourself. Second, you want symmetry. Okay, meaning if x equals to y, then surely y equals to x. So meaning what? Meaning this equalities, right, doesn't read the order. Okay, we don't have order of this equality. Okay. So last time is equal on what? Last time is equal on set, right? Now this equal on elements. Elements are very dangerous of that. Let me try here. Okay, wait, let me try first. Okay, so axiom 4 is what? You need transitivity. Mm. So transitive is what? If you take three things, right? Okay, if x equals to y and y equals to z means what? X equals to z. Okay, it can transmit, okay, the equal sign. And okay, let me try it back again without this cable. Okay, so first one, what we do is this set is a non-empty set. And then 2 to 3 is what we call the equivalence relation. So the equality here is an equivalence relation. Okay. Next, we're gonna introduce. Okay, am I skipping something? 1, 2, 3. Okay, so there's another equality here. So if x, y, okay, you take any two elements. If y is in this set we call natural number, and x equals to y, then x is in the natural number. So we want to bring everything that's equals to the elements inside the set into our set. So this is axiom 5. And then axiom 6, we will introduce a function called a successor function. Okay. Later, it will make sense why we call it a successor function. So for every n, we can define a function called s. And s apply on n, you still live in the natural number. Okay, still give you a natural number. So what else this successor function can do? So for every mn in n, m equals to n if and only if Sm equals to Sn. What does this mean? M equals to M, of course, imply Sm equal to Sn. This is function. But you have another direction. Sm equal to Sn implies M equal to N, meaning what? Sorry? Yes. So meaning this successor function has to be 1 to 1. Okay, cannot have two numbers get sent to the same place. Okay? 1 to 1. So this is about injectivity to 1. Axiom 8. Okay, so for every n in n, okay, we cannot send n back to 1. Okay, so we want to create more number with Sn. We cannot send everything back to 1 or any one of them back to 1. Okay. Next, we're gonna have 13 axiom. So next, this one is called the principle of mathematical induction. Okay, so how we gonna phrase this mathematical induction here? So if K is a set, okay, so let's say you have some set, call it K, and 1 is in there. And then for every n in n, if n in K, then S applies to n is also in K. Okay. And then this set will contain all the natural numbers. Later we'll see that this axiom is very powerful. Then later we'll see how we're going to use this axiom. If K is a set such that you can check that 1 is in there, okay? And then for every n, if n is in there, then Sn is in there. So this is normal mathematical induction. What do you do? Prove the base case. Okay, so the base case here is like 1 is in there. And then inductive step, hypothesis, you assume n equals to k is in there. So assume if n is in there, prove that n plus 1 is in there. So n plus 1 here refer to the Sn. Then your set will contain everything about this natural number. Okay. Yes, this is another variant of principle. This is the foundation of mathematical induction. Next, so why we call it a successor function? Because really we define Sn to be n plus 1. so it's a successor, n plus 1. So we're going to build, because just now we say what? For every n, Sn is in the natural number. So if you put S1 inside here, become what? 1 plus 1. 1 plus 1 is in the natural number. Okay. So 1 plus 1, we call it 2, for example. Okay. So now we only know 1 plus 1 is in n. But for future here, we call it 2. So what is 1 plus 1 is 2. Okay. So similarly, we can, for example, apply x to 2. So what happened? S2 become 2 plus 1. Okay. And then in modern day, we call it 3. Okay. So 3 is actually 1 plus 1 plus 1. Yeah. Okay. Yeah. So this is how we build a basic natural number. And so this one is about addition. Another addition we have is how to add any two number, right? Okay, so how to add two numbers here? So we will do it as n plus sm equals to x on n plus m. Okay, first of all, think whether this makes sense or not. What is sm? What is sm? Sn is what? N plus 1, right? Sm, n plus 1, right? All right, so let me make a footnote here. So let's make a footnote here. So n plus m plus 1. How about the other side? N plus m plus 1. Okay. So you see that both sides is equal, right? You should get equal answer. But what's special about this bracket style? Associativity. Okay, associativity on with what? Associative, right? Because you can compute the last two first, then you add, or you can do the first two first and then do the last one. Does it make sense? So this is associativity. Have you guys reached associativity in algebra? Okay, yeah. So this is associativity. But you see, associativity normally is 1, 2 with another unknown, right? But here we just start with 1 first. Because we know that 1 is always in our set. So we're going to build associativity out from here. Next, two more. Okay, two more. Two more will be about multiplication. So for every n in n, n times 1 is always n. This says what? 1 is what? The multiplicative identity, okay, of this set here. So axiom 13. Okay, axiom 13 is what? For every n and m, okay, so how are we going to multiply these two numbers together? So we will define on n times sm as well. Okay. Anyone want to guess what is this? Even you know sm is m plus 1, what is this? This should equal to what? So how I want to try? Try. N times sm is what? Try. Sorry? Yes. So this is m plus m. Okay. So we need all these to hold. Then the claim is we can build whole natural numbers. Okay, we can create every natural numbers out of these 13 axioms here. Huh? How? How? I mean, we won't prove it, but I'll briefly tell you how to imagine it. So you see, from this axiom here, somehow you're already building all the number you need already. But just you need to make sure that why these numbers are different. Why these numbers are different? Because you have a injective mapping. the S n equals to n plus 1 is injective. So you won't create degenerate number. So all the n plus 1 are different. Okay. Okay. Okay, let's try prove one thing. So let's say because we want associativity in our number, right? Because 1 plus 2 plus 3, no matter you do 1 plus 2 first and then plus 3, or you plus 3 plus 2 first plus 1, you should always get 6, right? So we should prove this property out of this axiom. So let's say we want to prove associativity, meaning if x, y, z in n, then x plus y plus z equals to x plus y and then plus z. Okay. Just now we know that this is only true for when z equals to what? From axiom, we know that this sentence is true when z equals to 1. Okay, but this z is a random z. Okay, so how are we gonna prove this? So you see, you want to prove for all n. Okay, you want to prove that it is true for all n, meaning you need to use some sort of you can use some sort of printing mathematical induction here. Okay, so how are we gonna play the trick here? So proof. Okay, so we'll prove this. So we'll define a subset K in n such that K are all the element in natural number, or sometimes we just call it numbers, such that for every xy in n, we have x plus y plus z equals to x plus y and then plus z. Okay. So we define this subset here. And we pick out the z such that the sentence we want hold. And then what's the thing left with? What we need to show? We need to show that this k is actually n. Right, because you see the statement at the top, x, y, z are random number in n for all. Okay. And then the k here, we need to show that all z in n works. Does it make sense? Does it make sense? Can it make sense or not? What we want to do? Yeah. So what we can do is we're gonna use this axiom 9 here. You see, if k is a set such that 1 is in there, okay, and then you verify that if n is in k and then Sn is also in k, then this k contain n, right? So you see, now I have k containing n. If I use principle of mathematical induction, I can show that k contains n. So what did I show? I have k is in n and n is in k. So together I got k equals to n, right? So k equals to n means what? Every natural number will satisfy the statement here. Does it make sense? Does it make sense what we're gonna do here? Is everyone following or not? Can follow? Okay. So we're gonna use axiom 9 here. So right, let me write down. So what we want to show is k is actually equals to n. Okay, using axiom 9. Okay, how to use axiom 9? Since our k is a subset of n by construction, right? We just pick any z that it works. So what we left to do, if we want to show k equals to n, okay, we already know k is a subset of n. What we left to show? N is a subset of k. Okay, then this is what axiom 9 can give us. K will contain the subset, the natural number. Make sense or not? Does it make sense? Okay, feel free to stop me. Okay, first, what we need to do, we need to show the base case. What's the base case here? We need to show that what is in K. Do you remember? The base case is 1 is in K. Okay, so we need to show that 1 is in K. So how to show 1 is in K? What do you need to verify? So where's my set here? So this is my set here, right? So let me make a highlight here. This is my set. So how to show 1 is in K? So you check for any x, y, you ask the question, is it true that x plus y plus 1 is equals to x plus x plus 1, x plus y, and then plus 1? Is this true or not? Is it true? Why true? There's the axiom of this, right? That's why we define this. So where is it? It is the axiom of 11. That's right. N plus m plus 1 Sm equals to Sm plus 1, which is m plus 1 plus 1. Okay, so that's why we include this axiom to be true, so that we have this base case to be true. Okay, so we need to start from somewhere, and then we take it as an axiom. Then this is true by axiom number 11. Okay, makes sense? Okay, all right. All right. Okay. Then this is true. Next, about next. Next, what we want to show? We want to show that if Z is in K, then SZ is also in K. Okay, so this is a inductive step. So let Z be K. Okay, and XY is in N. Then let's check. Then what? Then we have X plus Y plus SZ. We want to check that whether this is the same as X plus Y plus XZ. Okay. If this is equal, then SZ is in K. Makes sense or not? Okay. Yeah. So what we can do here? What can we do? What can we do? Can we move this successor function or not? Can we move it with this addition here? Let's check what axiom can move it. So for example, this successor function can move, you see. So this successor function can move before n if you include n and m together. Okay. Let's try and do this. Okay. You see, n plus sm is sn plus 1. So let's try axiom 11 first. Okay, let's try axiom 11, which tell me that I can move the s in front of y by adding y and z together. Okay. Can I do it again? Can, right? I can do it again, right? Okay, so I can move it s to the front again, such that become x plus 1 plus z by axiom 11 again. Okay. Here, x plus 1 plus z. Z is what kind of number? That is associative with s and y. So what can I do here? I can use the associativity of z, right? So I can do like x plus y plus z. Why? Why? Because z is in K. Okay, by assumption here. See, by assumption here. So you see, what I'm doing is I use axiom, I use assumption. So you need to be very clear about the assumption and the axiom you use. Okay, otherwise you will definitely get lost. Okay, so when you discuss question problems with friends, with others, right, you need to know what kind of assumption they take, what kind of assumption they make. Okay, then you only can use those assumptions and then you do stuff. Okay, otherwise you will see very random. Suddenly axiom, suddenly z in k. What is z in k? Okay, so you need to understand this statement. Okay, so are we good here or not? Are we good here? Can we go from the second last line to last line? Anyone see? By axiom what? Sorry.
Z is A, therefore Z is N because we find the subset.
What do you mean? I'm trying to go from the last line to, the second last line to last line. So yeah, so we're gonna use axiom 11 again, right? Does everyone see it? I'm using axiom 11. Why can I use axiom 11? Because x plus y is in n also. Is it clear that s plus n is in s plus y is in n? Is it clear? Is it clear why s plus y is in n? Is it clear or not? Actually, not so clear, right? It's not in the axiom. X plus y is in n. Right, because to use axiom 11 is what? You need to make sure that n and m is in natural number. But why is it x plus y is in n? Okay, let's try make this into a lemma. Oh, this one is a lemma. Why is it true that for every x plus y is in n? This is a similar question I asked last time. Okay, we define 1 as 1, okay, 2 as 1 plus 1, 3 as 2 plus 1, 4 as 3 plus 1. But on the other hand, we know that 2 plus 2 is also 4. So why is 2 plus 2 equal to 4? Using this axiom. So similarly, we need to show that x plus y is n. Okay. Let's try and make this into a lemma and then we discuss next time. Or whether you can do it yourself or not. Okay. So you need to show that for every x, y is x plus y is in n. Okay. So maybe we can discuss strategy how to prove this. Right. So we want to show that for every x, y in n, why is it x plus y in n? So out of these lemma, right? Out of these axioms, which axiom tells you something is in n? For example, 5. Tell you when is a thing is in n. When you know that some other thing is already in n, and then it is equal to the thing that is in n, so it is in n. Okay, this is one of the way. How about the other way? Axiom 6. If you can write x plus y as a successor of something, then it is in n. So these are the two ways you can show something is in n. We can discuss next time again. Okay. Yeah. Okay, if this is true, then we can use what? Where's the axiom again? We can use axiom 11, okay, to move x backward. move x backward, such that you get what you want. Does it make sense? Okay. So this is about associativity of natural numbers. Yeah, associativity. And so this is the first exercise we can do next time again. I'll let you try first. And another exercise is we can use similar method to prove distributivity. Okay, so what's distributivity here? So distributivity normally talks about two operations. Okay, two different operations here. So what are the two operations we have on a natural number? They are addition and multiplication. Okay, so how you do x times 1 plus z? Okay. This should be what? If you learn your high school, it's like open the bracket. So what do you get? Xy plus xz. Okay, so you need to use a similar method that we have just now. Define the set. Okay, then show that set contains n natural number, so that it is true for all n. Does that make sense? Or should I write down? So let me write down. Prove strategy. So how are we going to prove it? So similarly, we define k, okay, such that what? It is a natural number. It contains natural number such that for every xy in n, x times y plus z equals to xy plus xz. So what's the base case here? Can you see the base case here? Can you read out what's the base case? X times y plus 1 equals to xy plus x. Okay, so do we have this in our assumption or not? Do we have it? So let me write down what's the base case. Base case z equals to 1. So x times y plus 1 equals to xy plus x. So what is this? X times y plus 1 means what? S, y. X times xy equals to xy plus x. What is this? This is the axiom that, the last axiom, right? Just now, Lohao gave one, this one. Okay, so we have the base case. So that's why you see there's a reason why we include this axiom as our Peano axiom, because we need it to start the game. Does it make sense? Okay. Yeah, we need it to start the game so that we make it into axiom. Otherwise, I don't know why it's true. So I make it to be true. Axiom. Okay, so try and prove this on your own. So far, any question or not about this part here? Any question about this part? So a bunch of property of natural number can be proven this way. Okay, use mathematical induction. So I guess distributivity law haven't mentioned in abstract algebra yet, right? Because now you are just dealing with group theory. Group means what? There's only one operation there. But here we got two operations now, multiplication and addition. Okay, so we want to see how they interact. Okay, how they interact. Does it make sense? Make sense? Okay, what time is it? Okay, so maybe we go a little bit further and then we take a break. Okay, let's go a little bit further and then we take a break. This lemma, maybe we left to next time or later. See if we have time. Okay, so let's do something more relaxed. So we have number, let's say now, again, natural number 1, 2, 3, 4, 5, 6, and so on. Okay, so in your mind, what is 2? What is 2? 1 plus 1. What is 3? Sorry? Okay, you answer. Yes, 1 plus 1 plus 1. If you know 1 plus 1 is 2, then maybe it's 2 plus 1. And then 4. What is that? 1 plus 1 plus 1 plus 1 plus 1. Okay. Okay, good. Okay, so this is a new number in your mind already. Yeah? Okay, so these are the natural number. And natural number is good because if you grow a tree, right? If you have one apple, you have one apple. You have two apple, then you have two apple. You won't have negative number of apple. This is what I mean. But when you want to trade, when you do trading, right? Okay, I pay you money, $2, or I owe you money. I don't have $2 to pay you. So what? I become negative. Okay. So we can add negative of them into the system. And this is what we call the integers. Okay. So what I'm doing here, what do I mean by adding negative? What do I mean by adding negative? What do I mean by adding negative here? Sorry? Hmm? Yeah, minus. What do I mean by minus 1 here? You should think of it as the abstract algebra stuff. It is the inverse, and it is inverse of 1. It's the thing when you add to 1, you get additive identity, which is 0. Okay. So this here, what we are doing here, we are making it a group. We make natural number into a group. Okay, so this is what we call a group completion. Because we know we can add, right? We can add in natural number. But there's no additive identity there. What's the additive identity in natural number? There's nothing there. Actually, it's 0. It's the thing that we create 0, nothing. Okay, this is 0. And then from 1, how to get back to 0? There's no way. Okay, for natural number, there's no way. So we need to add this extra inverse into it. What is the inverse of 1? Minus 1. What is the inverse of 2? How to go from 2 to 0? Minus 2. Okay, so all the minus number are the inverse, additive inverse. Okay, for the natural numbers. Okay, so this is what we call a group completion. Actually, group completion is a very advanced notion. Okay, we complete it so that it has inverse, it has identity. Okay, so this is the integer. Okay, the famous integers. And next step, what can we do? We can go further. This is how I draw it. These are the rational number. So one way to describe rational number is simply P over Q. Okay, such that P is in Z, Q is in N. Okay, we put a negative in the numerator, such that, okay, that's all. That's all. Okay. So how we build this rational number? It's another group completion. You know what kind of structure does this rational number have? There is a multiplicative identity in natural number, right? 1. 1 multiply everything, you get back the thing. So 1 times 2, you get 2, 1 times 3, you get 3, 1 times 6, you get 6. But what's the thing that you multiply with 6? You get 1. This is the inverse. So what's that inverse called usually? Okay, reciprocal of 6. So 1 over 6, right? Okay, this is the multiplicative inverse. So this is how we introduce this rational number here. Okay, we add in all the, adding all multiplicative inverses of Z. Of course, we cannot invert 0, right? What is 1 over 0? Undefined. Okay, so we just invert everything that's non-zero. Okay, does it make sense? Or maybe you ask me, okay, I invert 2 is 1 over 2, invert 3 is 1 over 3, then 3 over 2 is also rational. So how to make 3 over 2? How to make 3 over 2? 3 over 2 satisfies this rational definition, right? Yeah, so how to make 3 over 2 if I just add the inverse? So what is 3 over 2? What's 3 over 2? You know 3, you know 1 over 2, so what is 3 over 2? 3 times 1 over 2, right? Okay. Does it make sense or not? Okay. Okay. 3 times 1 over 2, 1 over 2, correct, right? So meaning what? 3 over 2 is 1 over 2 adding 3 times. Okay, also makes sense. Okay. So we will skip the construction for Z and rational. Okay, this is I just quickly tell you how we think about this, and we will spend time constructing real numbers. Once we construct real numbers, we construct everything before it. Okay. Then once we construct real number, we construct everything before it. So I share you one slide that I made. I think it's quite cool for my abstract algebra class last time. Where is it? I will leave it in my lecture notes for you to read. Let me see here. So here. Okay. So I make a small summary here. Actually, groups is very important when we talk about numbers. So first of all, we start with the natural numbers, right? 1, 2, 3. Okay. And then we try to add in additive inverse so that you have -1, -2, you have 0 also. Okay, additive identity. And then you go to rational numbers by adding the multiplicative inverses for the non-zero element. Okay, you have half there, you have 1/3 there, 2/3, 3/3, 100/3. Okay. And then next we go to reals. Okay, this is the step we will spend time discussing about. So this is a thing we will discuss about later. Okay. We will construct this real numbers. And then after real numbers, going to complex number. What's complex number? It's just x plus yi, right? Such that s and y are in R. So to construct complex number, actually it's also algebraic. Okay, actually if you study much more later in the group theory, maybe they'll teach it. Otherwise, you will be in the AA2. Okay, construct real numbers, complex numbers. Okay. Then after complex number, you didn't stop. Actually, they construct some other numbers, which is quaternions. Why quaternions put a hex there? Why don't put a Q there or what? Because it's a guy called Hamilton that constructed this. Hamilton. And then you can go further to octonions. Okay. So how we describe this quaternions and octonions? We describe as some sort of a vector space. They are like, you see, so you see, complex number is like 2-dimensional vector space. But quaternion is like 4-dimensional. So ijk plus a constant. And then octonion got 1, 2, 3, 4, 5, 6, 7 plus constant 8. 8 bases. Okay. And then how they multiply, I just need to tell you what happened in the I and j and k multiply together. And this one I didn't list it down. It's quite a few relations here. You can go and search online on the wiki. And they summarize it in this picture here. They summarize in this picture. You can go and look for it. Yeah, so there are mathematics over quaternions, there are mathematics over octonions, and then of course mathematics over complex. This is what usually the engineering people do. Okay. And in this class, we will focus on mathematics over reals. Okay. Yeah. Does it make sense? Any question before we take the break? Any question before we take a break? Yes.
If constructing real mean we can construct everything before,
Yeah.
how can we construct this everything?
What do you mean? And construct real and then
We construct
Oh, you mean is it like you want to ask about non-empty thing, non-empty statement? Why is it like can we reproduce natural number or something like that or what?
No, because based on this graph,
Mm.
the materials for constructing reals is based on
Mm.
natural integers and rationals.
Mm-hmm.
Then doesn't that mean we have to use this to construct?
One way, okay. Let me tell you one way first. So one way is like we build reals using rational. That's what I put there. Cauchy completion. Later, once we learn Cauchy sequence, I will show you this Cauchy completeness. The other way is we just use structure. It's like how we build natural number. We just use structure. And then we build something that we call it real numbers. But is this the real numbers that we know from what we know, not like E, pi? Should those numbers inside there? Okay. Actually, this is a proof. Okay, up to some yes, we call it isomorphism. First of all, you should understand it as a bijection. There's a bijection. But this bijection is special. It respects structure. Later I will disclose more. Yeah. We define something resemble a real numbers. And then we prove that there's only up to the same structure, there's only one thing. Maybe I can use different symbol to describe pi, to describe E, but there's a bijection between those two abstract system. Yeah. Can you imagine or not? It's like how to say. It's like table. You see IKEA so many table, but why different shape also called table? Because they have the same function. Does it make sense or not? Maybe it's not exactly the same shape, same design, but still table. Right? Is the chair you sit here the same chair you sit at home? No, no, right? But why they call chair? You know? So what differentiate chair is the usage of chair. So what's the role of chair? If you can sit on that thing, probably you just call it a chair. I mean sit like now. Also maybe this become a chair, right? But maybe the old people tell you don't sit on the table. Okay. Okay, no. Yeah, so this is how we abstract things. Yeah, we will see. Okay, we will see. Any question before we take a break? Other question? Okay, so yeah, so really to appreciate these things, right? You need to ask why I need to write pi, why I need to write E, why I need to write one, why I need to write two. Okay, then you will appreciate why we set up all these axioms. Okay, so let's take a break to 107. Okay, and then we will start about real number. By the way, complex mathematics over complex number is what you're gonna learn next semester. Complex analysis. Okay.
情况下，60个，3个同时开，30是不是？那你直接讲讲为什么？看看，
你觉得这样比
问他哦，每次做几个就A FM 来啊，他来话，那个你说很多，
这样话就帮他说，我看到一个版本，
没有，这个是这样做错，
啊，
因为它里面是这个。
我看到一个版本，他讲，哦，我觉得 A 到
现在不懂嘛，
老师，
然后开始历史
我是第一，
大概是历史开始的，
是
那你的确不是但现在是很多
啊，不是，
那我会觉得
那时候是
更好的历史。
所以我觉得是没办法，
没有啊，上面在我的 keyboard 里面。
还是在6
哇，一个
对这个东西啊，对，反正这个东西它的
每一个它之后的它之后的东西就大过超越。
折算，那折算如果追求比如讲我的 A T 是否根本
哎，是在这个里边，
那我第一次他讲的是不是讲我会看的时候，也就是不要变成
可以
他没有管他对来属什么不一样的他跟前面不一样吗？看股票这样子，对啊，一开始的时候还没有起嘛，突然间冲了。
没有，
不管前面是因为细坤通常是理后面罢了，前面管他怎么去跳怎么去跳，到后面的时候，到最后面会停在一个纸上面的，会越来越靠近那纸上面，是它是上面，我指
他说你在解释，
一个顺序念，就是每一个 M 在 r 每一个 r 的歌呢，但是完全都会找到一个有，然后such that 它之后的那边，所以意思说，你从 A 大 A 开始，然后 AN 加1 AN 加2 AN 加3加4，任何东西都会 strictly 大于1还是3选。
选的这个号码是对，他是选的，
every one 怎么选 ？every 要每一个它能够让它变大， 你现在选100万1000的，兆。你看他讲 for everyone 你选1兆，1兆都还有一个 n 在上面，是不是还大过1兆？真不真？10兆的100兆1万兆的1兆。
这个也是选，
这个是 OK， 虽然是选，但是它是因为它的存在，因为它是顺序问题，顺序的问题发生了就会发生。对，每一个你都可以找到一个。对，
那没有关系。
没有关系，这样子看肯定是没有关系的，这样有什么关系？关在这里，关系是在哪里看？它这里才是个关系，这个才是关系，这个关系。什么 m 选存在一个关系？关在这里，它把大 N 把大 N 小 n 全部连在一起了，在这边。为什么大 N 跟存在这边？因为大 N 跟小 n 有关系，关系是在这里，前两句没有关系。是的，来问。来过去过的地方。没有。
啊，他这里写，他这里小一点加了。
对，如果是这样子写的话，你应该没有大于。来过去看，能来过去看。可以打回去下面，因为你这个是有问题。要写大于，要大于，只有选平的大于。哎，其实也不用哦，不一定啊，
它可以从数数开始往上。
对。然后 for every that exists，Seng. Okay, let's come back. Okay, let's come back. So, let's motivate why we want to find real numbers. Why do we want to find real numbers? Okay, why not we stop at rational number enough? So the theorem is square root 2 is irrational. Have you guys seen the proof? Square root 2 is irrational. And where? Which one? Seng. Oh, algebra and analytic geometry. Anyone remember how to prove this? Yes. So suppose on the contrary, because we want to produce the contradiction proof, so tell people first. So suppose on the contrary that square root 2 equals to m over n, such that, sure, more importantly, m and n do not have common factor. We cancel out, we simplified it. Okay. So we try to contradict this statement here. Later, we will find common factor between m and n. So what can we do? Then, what can we do? Square them. Okay, so we can get 2n squared equals to m squared. Okay. So this means what? This means m squared is a multiple of 2. But 2 divide m squared. Meaning what? Two is a prime. So 2 must divide n. Okay. So since 2 divide m squared, 2 must divide m. Does this make sense or not? Make sense or not? If 2 divide m squared, 2 must divide m. If I split 2, right? How 2 can divide? I mean, how to split 2? There's only one way to split 2. 2 times 1. So you cannot say 2 divide 1 m, 1 divide the other m. Okay, you can do that, but what I want to say is 2 cannot divide not divide the product of m without dividing m. Does it make sense? Does it make sense or not? You cannot divide the square of m without dividing m. Make sense? Okay. So meaning what? This means that what? M is 2 times k for some k. Okay. Okay. Because 2 already divide m. So meaning m is an even number. Okay. Then what? So 2n squared equals to m squared equals to 2k squared equals to 4k squared. Meaning what? Meaning n squared equals to 2k squared. Oh, again, n squared equals 2k squared. What can we say? Similarly, 2 divide n squared, which implies 2 divide n. See, 2 divide n, 2 divide m. Just now I said n and m, there's no common factor. But now you see 2 is a common factor. So this is a contradiction. So let me put here. Before this contradiction, what do we get? This implies that 2 is a common factor of. This is a contradiction. Okay, because we assume there's no common factor greater than 1. Okay, make sense? Everyone okay? So if I ask you to prove square root 6 is irrational, you know how to prove? Try similar method. Okay. Okay, maybe put an exercise. I think this is also one of the exercises in the book. I'm not sure. Square root 6 is irrational. Okay, so where does this irrational come from? Where does this irrational come from? So I go on Wikipedia and then check it out. So rational come first or irrational come first? Rational, you guess it's rational. Actually, Wikipedia says it's irrational. There's a reference there, maybe you can check. So it came from these what Euclid works. Okay, it says that a number is this thing. This Greek word here. What is this Greek word here? This is logos. What is logos? Logic. Okay. In Chinese, it's Dao. Dao. And Dao is as in the Dao Jia Dao. Dao De Jing the Dao. Okay. So they also value this logos. Okay. Logic. E-logic. Okay, E-logic, non-logic. So we call it irrational. Okay, so it said that rational come from irrational. Okay. Only then the ratio comes up. Ratio comes from rational. Ratio is like P to Q, P to 1 to 2, right? 1 to 2. 1 to 2 is like 1 over 2. Okay, 1 over 2 is rational. And then rational comes from irrational. Because why? Why is this irrational comes up? Have you guys, I think I mentioned this story to you guys, right? Anyone still remember the irrational story? Don't know? You know the first guy that found this irrational number, what happened to this guy? Die. Why die? Everyone will die, right? But how he died? Huh? Got killed. Got killed. Killed by who? Not Seng. Pythagoras. Not Pythagoras itself, but it's the Pythagoras branches, the students of Pythagoras. Okay, at that old time, Greek times, they think that rational is enough to explain everything in this universe. These are all the nice numbers. But somehow the contradictional proof by contradiction. Proof, there's something that cannot written as the ratio. The people got killed. Gotta be careful. Careful. It's not saying that you cannot say the truth, but be careful when you try to say some truth. Okay, so that person get killed, and then what? And then, and then that person get killed. But actually, you know, without this person, right? We don't know about pi. Actually, pi is irrational. I asked you to prove in calculus too, right? Did I ask you to prove pi is irrational or e? Pi or e? I forgot. Pi. About Fourier series, right? Yeah, pi is irrational. But circle is a thing that occurs in various places. You can draw a circle here. You see that this one is a circle, is it? How to draw a nice circle? You need a pi. Yeah, so there's some ratio governing the circumference and the radius, or the area with the radius. The ratio is pi. It's irrational. I cannot write as m over n for some m and n in integer. Okay. Yeah. So irrational. So next. So this is about. So it seems like there's a gap. There's a gap between rational, because we can find irrational there. We can find irrational number. So can we fill out this gap or not? Okay, so let's see how we fill out the gap. Okay. So similar to how we build natural number, we will also build real number using axiom. Okay. So there are 3 groups of axiom we will talk about. So first of all is a field axiom. Okay, so this one will explain what things are called field. And then second is the order axiom. So we want to talk about 2 is greater than 1, 2.1 is greater than 2. Okay, we want to talk about this order. And then third is a very important property of real numbers, which is completeness axiom. Okay, so how complete is it? Okay, complete in what sense? Okay, we will talk about this. So these are the 3 axioms that characterize real number. Okay, so just now, Joshua asked, if we don't know about natural number, don't know about irrational number, can we still build reals? My claim here is yes, we can build reals. Maybe it's not in a number form, maybe. Okay, I don't know why it's pi now. But as long as you have this structure, then this is a real number. There's only one real number up to some special bijection. Okay, we call it isomorphism. which is a field isomorphism. Have you guys learned group isomorphism yet? Not yet. What things you guys learn in right now? Groups. Stop at definition of groups. Where do you guys stop? Huh? Oh, commutative abelian groups. Stop at abelian groups. Okay. Then later, probably, if not, you ask to leave. You should learn map between groups, which is called homomorphism. Okay, map between groups. And then bijective homomorphism is called an isomorphism. So it's a bijective group homomorphism. But here is a field, not group. So what's the difference between field and group? We are interested in more than one law of composition. Did you guys learn law of composition or binary relation? Which one? Binary operation, huh? Okay, yeah. So there are two binary operations in reals. What can you do? Add, multiply. Okay, these two. So it makes up field. Okay, but more generally, it is actually a ring. I think you guys will learn ring after group. Okay, you will learn a set with two binary operations. Okay, but now we will just introduce it as an axiom first. So what sort of property in axiom of field? So let's list down property of field axioms. So I will list it in the table form, not in the sentence form. So it's easier to compare and have a summary. And this is also the practice in Petrovic, okay, the Petrovic textbook. So there are two binary operations here, addition and multiplication. Okay, what do you expect in group? You will expect it here. So tell me, group definition. The first thing you need for group. Closure. Okay. Second thing, associativity. Very good. Okay. Anything else? Good identity. And then inverse. I think that's all. Okay, you learn for group. And then here we are stronger than a normal group. We want abelian group. Okay, so we want commutativity here. Okay. And then you see there are two operations here, right? So two operations here, we need to take care how they react together, how they what's their chemistry? They have to be a distributivity law here. Okay, so let's list down exactly what this word means. Okay, so closure means what? If I have two things in my set, okay, I don't know these are number. If I define an addition there, it is still inside the set. So this is closure. Okay. Similarly for multiplication, if I have two elements in this real number set, I multiply them, I still stay in the real number set. Okay, so this is closure. Associative, A plus B plus C equals to A plus B plus C. Similarly, AB times C equals to A times BC. Okay, and then identity is what? So the identity element for additive, we will say to be 0. Okay, so what equation I need to satisfy? A plus 0 equals to 0 plus A equals to A. Similarly, I have A times 1 equals to 1 times A equals to A equals to 1. Dangerous. Huh? Okay, and then inverses A plus minus A. Okay, so we don't see negative as minus now. Okay, we see it as an inverse. Okay, A plus minus A equals to minus A plus A. Okay, so in our mind now, we only know how to add. We don't know how to take negative. Negative is just the inverse of the element. How about inverse for multiplication? A times A inverse equals to A inverse times A equals to 1. If A is not 0. So you see, why why we have these two kind of order? Actually, there's a special name for this. So the first one, a plus minus a equals to 0, means that minus a is a right inverse. You add from the right, you get 0. And then the other one is left inverse. You add from the left, you get 0. So if left inverse and right inverse exist, you can prove that actually left and right inverse are equal. You can prove this. Okay, if left and right exist, both exist, then they have to be equal. Okay. Have you guys proved that the inverses are unique or not? Not yet. You can try and prove it. Inverses in the group are unique. For example, why in the world there's not a second minus 1? Why there's only 1 minus 1? Did you ask this question or not? Why there's only 1 minus 1? Why there's no other minus thingy at 1 you get 0? Because you can prove from the group property that inverses are unique. Okay, inverses are unique. You can try and prove this. It's a very quick exercise actually. Inverses are unique and very important. Okay, commutativity. A plus B equals to B plus A. Okay, and for multiplication, AB equals to BA. For distributivity, anyone want to guess? A times B plus C equals to AB plus BC, AC. Okay, yeah. So I didn't put a quantifier here. You should take note that these are true for all ABC. Okay, true for all ABC, no matter what element you pick, should be true for all. Okay, so this is a few axiom. So, okay, any question about few axiom before we continue? No? Okay, all good. Okay, so these really come from groups, a generalization of groups. So already from this few axiom, okay, we already have a few nice consequences. Okay, so let's give you an example. Let's see what we have. You can see a lot of nice property that you can do when you do calculation follows from this axiom. So let's see. So real take away 0 means what? This real number set, I take away the additive identity. So from this few axiom, what did we assume? We already assume there's 0 inside there. We already assume there's 1 inside there. Okay, these two things inside there. But we don't know it's the usual 0. We don't know it's the usual 1. What we know about 0 and 1 is they are additive, inverse, and additive identity and multiplicative identity. Okay, it's the thing that do the job there. Okay, we don't know it's the 0 or 1 in the natural number. It's not like that. We just know the property and how it interact with other element. Does it make sense? It's not 1 ringgit, 0 ringgit, not like that. It's just something that when you add to 0 is the thing that when you add to anything, you get back yourself. Okay, and then 1 is the thing that when you multiply with everything, you get back yourself. Okay, this is the thing we know about 0 and 1. We don't know whether 0 is bigger, 1 is bigger. Later we will prove 1 is greater than 0. Okay. Okay. So this now you know nothing about 0 and 1 other than their identity. Okay, later we'll see actually 1 has to be greater than 0. We'll prove it. Because you are in a mathematics class, right? You should know, you should prove this kind of thing. Okay? 1 is greater than 0. Okay, later we'll prove this. So, what kind of a nice property we can get here? If AC equals to BC, what can we do? In the normal number setting, A equals to B. This is actually, there's a name for this. This is called a cancellation law. Later you will see this again in a group algebra class. Okay, cancellation law. You can cancel C on both sides. Okay, we will prove why is this whole. And then A times 0 Because just now we only know how to add to 0, right? How about A times 0? It has to be 0. But I didn't tell you in the axiom. It's implied by the axiom. A times 0 is 0. Okay. Does it make sense? Okay. And then what else? You know minus A. How about minus A? So in your high school, right, you take for granted. Minus plus minus, plus minus minus, minus minus plus, minus minus plus. So this one get A. No? But why is it A then? Now I teach you. Minus A is an inverse. Inverse of an inverse. Come back to A again. Okay, inverse of the inverse. Okay, for another inverse, there's another kind of inverse. It's the multiplicative inverse, right? So if you learn in your high school, right? So if you put a minus 1 on the fraction, you swap, right? Okay, so you swap twice, and then you get back to C. 5. How about 5? Minus 1 times A. Minus 1 is the inverse of 1. It makes sense. A also makes sense. These two times together is what? And in your high school tell you also minus A. Why? Minus A is inverse of A. So you take inverse of 1, multiply A, get an inverse of A or what? No, okay. Not so clear. 6. 6 is normal stuff. A times minus B equals to minus AB equals to minus AB. Okay. A times minus B. A times the inverse of B equals to the inverse of AB. Also equal to the inverse of A times B. 7. If you take 2 inverse add together is what? In high school, I think they will tell you to factorize the minus 1. Factorize, right? Okay, so y become an inverse of A plus B. Okay, factorize. What else? So maybe I'll just list out in a table first, in a page. So 8. What is 8? So if you take the 2 inverse multiply together, you get back AB. Okay. You factorize or not factorize, you just move the minus 1. Right? And then A over C times B over D. Why is it true that it is AB over CD? And then 10 A over C plus B over D. Why is it true that AD equals plus BC? So the last two is like defining the addition and multiplication on the rational number. So it's a result from the field axiom. Okay, it's a result. How many field axiom we have? 1, 2, 3, 4, 5, 6, 7, 8. So let me see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, and then you can do these all sort of things. Okay. So let me show you some example how to prove, and then later we split into groups, and then you try and prove some of them. Okay. So me show you some example. Maybe I show you 1 and 2. Okay, let's do 1 and 2. Let's do 1 and 2. Okay. So let's do 1 and 2, and then later we split into group and then try and prove other stuff. So first we want to show that AC equals to BC implies A equals to B. Okay. I think this one is fairly straightforward. This is what you also do in your normal maths calculation arithmetic. So what do you do? Suppose first AC equals to BC. Okay, I want to get A equals to B. What can I do? I want to get rid of C, right? How to get rid of C? Multiply by C inverse. Does C inverse exist or not? Exists. It exists for all C which is non-zero. But this C here should be non-zero, you see? C and D are non-zero. Okay, so since C is non-zero, okay, the inverse says what? If it is non-zero, you have an inverse. Okay, so there exists C inverse such that C inverse, C inverse C equals to 1. Then we can multiply on both sides. So maybe consider A. Okay, maybe we be more rigorous. A is what? A equals to A times 1. Okay, we don't want to use a multiply on both sides. Maybe it's not very justified. So let's do this way. A equals to 1. A equals to A times 1. And then we want to end with B. Okay. A equals to A times 1. Equals to C times C inverse. Okay, this is what we have just now. And what can we do? What can we do? We want to use the assumption AC equals to BC. But you see, A and C differ by a bracket. How then? Yeah, good. So we use associativity of multiplication. Okay. So in this mind, maybe you ask me, hey, Seng, got 10 field axiom, how to remember? How to remember? You ask me, I also don't know how to remember. But you just remember what you can do with real numbers. Then the field axiom will make sense. Do you get what I'm saying? How you manipulate real numbers in real life, that is the axiom we take. Okay, can we do like 2 plus 3 equals to 3 plus 2 or not? Yes, it is commutative. Okay, is it associative? Yes. Okay, so you should think like that. Okay, not just by memorizing. Okay, so AC. So this one is by associativity. Okay, the previous one is by inverse of C. Okay, the first one is by additive identity. So make sure in your assignment test, please write each step y equal. What have you used? Okay, otherwise you will easily miss something. Okay, first line y is it true? Okay, by additive identity. Second line y true because C inverse is the inverse of C. Third line y true, it is because of associativity of multiplication. Okay, and then we can use the assumption now. By assumption. Okay, we swap AC become assumption. AC become BC. So how to get rid of the C? How to get rid of the C? Again, we use associative. Okay, and then you can see that we are sort of like doing the reverse job, right? We are doing the reverse job here. Okay, we are doing the reverse job here. Okay. Okay, hold on. So you see, multiply on both sides actually contain this step. Why you can just multiply on both sides? Multiply on both sides. Then true. You see, contain this step here inside here. Okay. Does it make sense? Makes sense. Okay. So you see, you cannot. Okay. So by this, you can say that I can multiply on both sides. Actually, this is what you are doing. Okay. So my practice is usually when we want to show something is equal to the other thing, right? We start with one side, A, and then equal to B. Okay, then A equal to B. And then in the middle, what you can use is what the axiom allows you to do. Okay, good. So this one is cancellation law. Let's do a second one before I let you go and discuss. So let's show this. Why A times 0 is 0? It's not like A times nothing is nothing. So why A times 0 is 0? What property can you use here? What property can you use here? What property can we use here? Yes, that's right. So how are we gonna use distributivity here? We need to make use of this 0. 0 plus 0 is what? From 1 0 you can get 2 0. This is amazing. You know, 1 plus 1 is not 1 or only 0 plus 0 is 0. Okay. So we need to make use of this. Okay. So let's try. A0 plus A0 is what? We know this, right? Because we know distributivity law. Okay, how are we going to distribute this? Maybe there are two ways to distribute it. Do we have two ways to distribute it? Yeah. Okay, how are we going to distribute this? Roland, try. How to distribute this? How you want to distribute this? Wait, say again. A bracket 0 plus 0. Good. Okay, so maybe we try this first. What's 0 plus 0? 0. So we have A times 0 plus A times 0 equals to A0. What else can we do? We can do addition on both sides. What can I add? So just now I said cannot simply add, right? So you need to go through the argument just now. So let's say we can do it now. Add what on both sides? There are too many things here. I want to get rid of some of them. I get rid of the A0. So I add the inverse of it. Both sides. What do I get? A0 plus A0 plus minus A0 equals to A0 plus minus A0. What do I get now? But some subtlety here, you see. Sorry, there are some subtlety here. Yeah, right. Before that, you see there are some subtlety here. We add A00, A0 first, and then we add minus A0. So there's some associative you need to do first. Okay, to be precise, you need to do. So let me put here. Here I say a bit unprecise, and no, not imprecise. I'm not imprecise. Imprecise, right? Imprecise. Okay, a bit imprecise here. So let me do some shortcut here. So let me say this is a shortcut. So I can associate. So you have an element add with its inverse. What do you get? You get 0. Okay, so you get A0 plus 0 equals to A0. What is A0 plus 0? A0. Okay, so big on the other side should be 0. Sorry. Okay, so we get A0 equals 0. Okay. So easy to remember. People will say, oh, you have nothing, you get nothing. And so what's this nothing? This nothing is the additive inverse. What do I mean by nothing? Is the additive inverse. Because you add to it, you get back yourself. You're really adding nothing. Right? Does it make sense? Make sense or not? Okay. Okay, so you see here I put shortcut here or imprecise. Try and write it in this form here. Can you write it in this form? A0 equal to something and then equal to 0. Can you write in that form? Okay. Try and write in this form yourself. Does it make sense? Do you know what I'm saying? Yeah. Try rewrite this argument adding on both sides. Okay. Using this equality. Okay. Yeah. Okay. Okay. Try and do that yourself. Okay. So we have what else? We have 4, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So these are in order, meaning you can use the previous statement that we proven. Okay. So for example, if you want to prove 5, you can use 4, 3, 2, 1. Okay. So how many people here? 14, right? 14. 3, 4, 5, 6, 8. Okay. Maybe two in a group. Okay, two in a group. Jinsen and Larry, and then Huanye and Ethan, and then Sydney. Yes, Sydney with Yanru. Okay, and then know-how with Han Wei. Okay, know-how with Han Wei, and then everything. Wait. So how or here got one more like this. Okay, so Ivan with not Jack, behind Jack. Yixing, yes. Ivan with Yixing, Jack with Roland, and then Joshua with Yuan. Okay, so here from here, you guys prove. Okay, Larry have to do more job. Okay, Larry have to do more job. Okay, let's let Larry team prove 9 and 10. Okay, 9 and 10. Okay, and then Joshua 8. Okay, Joshua group 8, Ivan group 7, and then Roland 6, and then Dohao 5, and then Sydney 4, Sydney team 4, and then Ethan 3. Okay. So if you finish, okay, I give you 5 minutes. 5 minutes to do. If you can finish yours on time, then try the next one. Okay. Yeah. Okay, I give you 5 minutes. Discuss with your friends how to prove it using Axiom. If you need the Axiom page, I can scroll up for you. Okay, I can scroll the Axiom for you. Seems like some of you got it. Try and prove other. I think we have 2 more minutes. Oh. Okay, we can try and start now. We have quite any time. All right, let's start with 3. Okay, because these property actually are in order. The difficulty is in order because you use the one that previously proved. Okay, so who is doing 3? Number 3. Okay, so Ethan or Kuan Ye want to tell us what you're gonna, how you're gonna prove this minus a. The inverse of a is actually a. Okay, so because we are showing equal, right? So using the technique just now, how do you what step do you use? Yeah, to show a. So what do you do first? Can you do it in this way or not? Can you construct your argument in this way? 不是这么搞啊，OK？那看看你怎么搞。OK，好，不这么搞，我们把它收一边，可是我们再这么搞。OK，先看看你怎么搞，来。Sorry, A is equal to 0. Okay, good. So this is true for every A, right? Okay, this is true for every A. Good. This is what axiom is this? This is the inverse, additive inverse axiom. Okay, and then on both sides. Okay, so we add on both sides. So we use the similar technique just now. Okay, and then yes. So yes. Does everyone listen to what she said? So on the left side, what happened? We can do associativity so that we add minus a with minus a, and then we get 0. Okay, and then we on the right hand side we just get minus. Okay, so a equals to minus. So I mean you can turn into this argument, right? This kind of argument, step by step argument. How to do? You just add this whole thing. I mean, you just do this plus 0, right? And then you create the first line you need, right? You create the first line you need. Plus minus a plus a, right? And then similarly, it follows from what you said just now. Okay, you do associativity, okay, and then you get 0 plus a. Okay, yeah. So multiply on both sides actually means this left hand side equalities. Okay, does everyone follows? Everyone follows? Okay, Okay, so let's do 4. I don't fill in the step-by-step thingy. You make sure you know what axiom we use. Okay, right, fill it in. Okay, please fill it in your assignment because I need to know whether you know or not. So in future, you can skip it. But when the moment you learn, you need to write step by step. Future, you just do what I do here. Okay, make sure every step you do is correct. 4, we want to show that C inverse is C. Okay, so we have Sweeney, right? Sweeney and roll and yet root. Okay. So what are you doing first? What do you do first? Do you use my method or use like a Kuan Ye multiply on both sides? Which one you do? What do you do? How do you start? Any one of you is fine. Don't know how to do. Have you tried? Can you show me, what did you try? Can I see what did you try? Oh, you mean you let it to be D? Mm. Oh, right. Yeah. So you want to show that D inverse actually is C, right? Yeah, but yeah. So what kind of axiom have you used? Only this one, C inverse C equals one. This one is still true. Let's see. Seems like 1 point. But you cannot assume this time, right? Did Ian try anything else? No. Okay. So I haven't quite get it. So let's see. How are we going to show this time? What does it mean by C inverse is C? Means what? Meaning what? What does C inverse do? What is this thing? This is the thing that when you multiply to C inverse, you get 1. This is 1. This is the since C inverse is an inverse, or to be precise, multiplicative inverse of C inverse. Does it make sense? Make sense or not? Okay. And then what can we do? This is quite similar to part 3 already, right? What I can do is multiply on both sides with what? With 1. With C. Right? Because we want C. Okay. And then we use associativity again. Okay. Then we get C inverse equals to C. Okay. Does it make sense? Okay or not? Yeah. So you see, this one is still multiply on both sides. Multiply both sides by C. So can you write it in this form or not? Okay, start from one side and then end with the other side. Can you write in this form? Okay, this is very important. Although I allow you to do multiply on both sides in my class. Okay, so next, who's next? Who is 5? Okay, like Lohao or Hanwei. Yep. So 5, we want to prove -1 times A actually is equal to -A. So how do you do it? You start with what? Yeah, try. A 0? Okay, equals to what? Okay, wait. So are you starting with -1A equals to -1A times plus 0? Huh? Oh, you mean inside? Okay, sure. Okay, and then sure. -1 times 0, right? Good. And then sure. Like this. Sure. You still come back with -1 times A here. Yeah, so you come back to the same spot now. You haven't really go far yet. So this is where you guys stop, is it? Okay, good. Okay, good. So Yeah, so what kind of trick we can play here actually? What kind of trick we can play here actually? Expand 0. I think that's a good idea. Expand 0. It's a good idea, expanding 0. Do you have some concrete way?
Expand A plus one minus A.
Oh, okay, let's try your strategy. You mean A plus minus A like this? Okay, and then what else I can do? I'll get -1 times A plus -1 times the whole thing. And then do you want to further distribute? You want? Okay, you want further distribute. So -1 times A plus -1A plus -1 times minus A. Actually, this one we still don't know. Okay. Yeah, so then what else we can do? How do we get A? How do we get minus A? Is there a way to do it? We can further distribute, right? Hmm? Correct or not? Yes. So we can do -1 times A plus A minus A. Oh, this is not useful. We go back to the same spot. Insert the minus A. How do we insert the minus A? Insert where? Very beginning. So how to insert? Add of time. Yeah, so you need to tell me one concrete way. Where both sides? Both sides as in where? Huh? Where's the both side? Yeah. So how you think about this question? How should you think about this question? What is minus A? Minus A is the inverse of A. So what do you need to prove? What you need to prove is y -1 times A plus A should be 0. Why is this true? Huh? Why is this true? Because I can do this, right? So now I'm okay. Here, what am I doing is I start from goal. Usually people end with goal, right? I start with goal. Okay, this is all I want. I want this to be true. Minus A plus A is 0. Because I want to show that -1 times A is minus A. Because minus A is the thing that you add to A, you get 0. Okay, I start with goal. Okay, why is this true? Because I can add minus A to both sides. Okay, and then I have minus times A equals to minus A. This is what I want. Yeah. Does it make sense? Why does it make sense? Why does it make sense? Yeah, how do I know this last line is true, right? Still not good yet. Still not good yet. Yes, you want to try?
-1 times A.
Okay. Yeah. So what you want to do? So fail 3 times already. Okay, let's try the 4th time. Okay.
First, use additive identity at 0 to 0 to equals to -1 and A from 0.
Like this?
Ah.
Okay.
And then 0 can also be written using an inverse with -1 plus A plus bracket A plus negative of A.
Right. So is this what you want? Negative A plus A? Okay, like this. Okay.
We would write it as A plus negative A.
Sure. Do you want to use associative later?
Then associativity to get -1 times A.
Yeah.
A inverse.
Yep. At least.
And then using multiplicative identity, it can be written as 1A.
Hey, wait. What? Say again. Oh.
Yeah.
Oh, okay. Yeah, sure. Good. Okay.
And then distributive.
Mm-hmm.
-1
Mm-hmm.
plus 1.
Yep. Times A. And then you get 0 times A. And then you get 0 plus minus A. You get minus A. Okay, this is good. But take note here, you see, distributivity law here is on the right. Yeah, on the right. And then the 0 times A is also on the right. But whatever we proved just now or axiom is on the left. But note that our number is commutative. So you should be able to prove the left distributivity from the commutative. Okay. Does it make sense? Make sense or not? Make sense, huh? Okay, let me show you. So you see, let's look at this one. Okay. I want to try and deduce B plus C times A. Okay, I want to reduce this. How to deduce? Because multiplication is commutative, so I can commute both BA equals to CA. And then I can just define this right commutativity. Okay. 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 So that's why we just write left distributivity. Right is implied by the commutativity. Okay. Similarly, you should be able to prove 0 times A equals 0 as well. Okay, left and right. Okay, good. So we have 5. How many to go? Can we finish? Should we take a break? Let's take a break. Or should we finish? Do you want to finish it first or you want to take a break? We still have 1, 2, 3, 5 to go. What? Like that? Okay, let's prove 1 plus 1 not equal to 0, then we will end this lecture. Can or not? Okay, let's take a break. Okay, let's take a 10-minute breaks. 10-minute break. So we end at 1 plus 1 not equal to 0. So we end at here before we break. Finish class. Okay. Let's break until 18. 2:18. Okay.
给在读书。我这个这个钱我们在因为我刚写了题目，你知道我有这边有题目，这边有题目，这个这如果有这个文字上一起，先给你提的，这里你等于到
可以可以。
两个边就可以。这个数字
好，
好，这个这个。学起来。这样子，对不对？平常。
第九题。 You guys still trying, or can we start earlier? If we end earlier, then we end earlier. We start? Okay, I'm ready. Okay, so who is doing 6? Who is doing 6? Who is me? Jack. Okay, Jack and Roland. Okay, so how do you start with 6? Use what? Use what? Theorem 5. Okay, so how do you start? A times minus B equals to A times minus 1 times B, and then what? Associativity. Okay, good. So we associate A with minus 1, and then commutativity. Good. Minus 1 times A times B, and then associate again. Associate. Okay. So you see, if he say associate, I don't need to ask him how to associate, because there's only 3 things here. If you want to do different thing, there's only one way to do it. So I don't need to ask him where to do the associativity. So minus times AB, and then use 5 again, and get minus AB. Okay, I think this is good. And then you move it back again. Is it? Move to minus 1. I mean, move to B. There's another sentence, right? Minus A times B. So you, where should we go? Oh, actually, we already passed through already. Here. Yeah. Okay, good. So we already passed through that thing. So this is also minus A times B. Okay, good, very good. Use 5. Good. Next, 7. Who is 7? Okay, Ivan and Yixing. So how do you start? 2 answer. Can try one for them first. Start from what term? Left hand, so minus A plus minus B. Okay, equals to what? You also use 5, okay? So pull the negative out, is it? Okay, good. And then use distributivity. Plus 1, 0. You want to plus 1, 0. You want plus 1, 0? Okay, let you plus 1, 0 first. I want to see what you're doing. Okay, I want to see what you're doing. Actually, we see the answer already, but what are you doing? I want to see. Oh, okay. Is it helpful? Doing A plus B plus minus A plus B. Okay. So then
I use
commutativity.
A plus B inside a go at the center.
Then
Use the causative to let the minus A and plus A together and minus B together become 0.
Wait. Oh, so you mean like this? Minus 1 times A plus A and then plus B, huh? Oh, wait, let me think. What is it doing? Oh, yeah. You need 2 associativity here. Okay, good. Okay, you need 2 associativity, and then I see what you are doing. Then you go 0 plus 0 plus this thing, right?
Yes.
Okay. Actually, we can finish it in the second set just now. Right. Okay. So just now here, already you can do something here quickly. Actually, what can you do here? you can distribute already A plus B here. But you can use 5, right? You can use 5 become minus of A plus B and done. Okay. Yeah, but yours also work. But we will prefer a shorter solution. Okay. Yeah. Okay, good, very good. Well, where's your second proof? Oh, the shorter one is the shorter one. Yeah, that's right, that's right. So meaning you don't have 5, then you need to go through this long stuff. Huh? But if you have 5, then you can use 5 already. Yeah, the purpose of 5 is that. Yeah. Yeah, true. You are true. Yeah, what you do is actually proving 5 already. So that's why so you see, that's why mathematicians like theorems a lot. If you don't have theorem, you need to write this long stuff. If you have theorem, apply is Ivan's approach pure axiom. Pure axiom. You mean just using axiom? Huh? Yeah, pure axiom. Yeah, but in the middle, actually, you are using the abstract idea that minus 1 times A plus B is minus A plus B. But actually, you are already using it in the first place already. Hey, not pure, actually, sorry, Joshua, not pure, because first line is already not pure. First line is not pure. Unless, unless you don't pull the minus 1 out. You don't pull the minus 1 out, then you use whatever you say there. It's still true. Correct? Because you see, in the end, you need to put the minus 1 back. So meaning Ivan's approach can be made into pure axiom without pulling the minus 1 out. Okay? You just regard minus A as minus A, not minus 1 times A. Okay, then this is a pure axiom. But you see, this long step here actually hiding another truth, which is minus 1 times A equals to minus A. Actually, this is the truth that you need to search for inside this calculation. So this is mathematics. No? We keep proving theorem. Why we keep proving theorem? Because we found there's another truth inside this long calculation. This is what mathematics do. You have a long calculation. What? It works. Why it works? Oh, actually, this small thing works. And this is what we do. You get what I said? Don't just look for method, look for method. You need to ask why this method works. Oh, actually, this number 5 work. Then the whole method just shrink to 3 lines only. Otherwise, you need to go through 1, 2, 3, 4, at least 4. Okay? Okay, so this is the advantage of doing pure maths. Okay. So 7, 8. Okay, 8. How about 8? Who is doing 8? Who is doing 8? Yu Yan and Joshua. So prove that minus A times minus B equals to AB. Okay, how to prove? How do you start? Okay, you mean like this, minus 1 times A minus 1 times B, like this? And use 5, right? Use 5 twice, then?
Commutate A and minus 1 in the middle.
Sure. So before commutating, right? Actually, we need to do some associativity first. Okay, do associate and then do commute, and then actually have to associate again.
Minus 1 times minus 1 becomes minus 1.
Oh, like that. Okay, also can. We haven't proved minus 1 times minus 1 is 1, is it? Okay, sure. So CC, okay, sure. So 1 times A times B, and then AB. Correct. Okay, good. Okay, very good. Hey, very good. How about next? By the way, please go back and fill in the thing that we use. How many times we use associativity, how many times we use commutativity, and so on. Okay, proof 9. Again, 9 and 10 at one go. So let's prove 9 first. So things there are 2 of you, right? One of you talk about 9, one of you talk about 10. No? Okay, so who want to talk about 9 first? Henry, yeah. Then Jingsen talk about 10. Okay. How to prove? Start with what? Sure. So we should really define what is A over C. How should we define A over C? Any idea? A times C inverse. A times the inverse of C. Or really it's the same as C inverse times A because everything commute there. And then? So you start from left-hand side or not? Okay, let's start from left-hand side and then apply definition. Okay, apply definition. What can we do next?
Use associativity of AC inverse and then E and then D inverse.
Okay, maybe something like this. Is it? Okay, something like that. Apply a few times. And then? Okay, the associativity so that we get AB times C inverse D inverse until we do this. Okay, is this enough or not? What's the endpoint? Let me write down the endpoint. Endpoint should be AB times CD inverse. Right. So what's the difference between these two lines? It's just the last 2 alphabet. So we need to make sure the last 2 things are the same, right? All right. So we need to establish that. So lemma here. We need to prove that the inverse of CD is actually C inverse D inverse. Okay, how to prove this?
CD. CD is the C inverse of CD is CD inverse. Like basically the obvious one percent. And then after that, we claim that
So let's prove it. Okay, let's prove it.
let's observe CD multiplied bracket multiplied by this one plus this one by definition of inverse that is given as 1. And then we will observe that if we have CD times C inverse D inverse.
Oh. Okay. Okay, so not that this is true. Okay, also CD times C inverse D inverse. Why is it 1? Okay, let's calculate this. Why is this 1? Okay, associate whatever how you want to associate and then commute. Okay. And then we get 1 times 1, which is 1. Okay. So here, be careful. Inside here there is associativity, commutativity. Okay, please write them down step by step. Okay. And then how does prove that CD inverse is C inverse D inverse? Yeah.
Symmetry and transitivity of equality. We have CD times CD inverse equals to CD times C inverse D inverse.
What was by symmetry and transitivity?
Because they both equal 1, so and because equal is equivalence relation, we can say those 2 things are equal.
Okay, so this implies that CD inverse equals to 1, which is equal to CD C inverse D inverse, sure. And then
We still basically we can apply cancellation law for multiplication. C and D are
yeah, okay, so apply cancellation law. Okay, so cancel. But just now we cancel on the right? So you also need to prove whether you can cancel on the left or not. But you just use commutativity. Okay, or you get CD inverse equals to C inverse D inverse. Okay. Otherwise, you can just multiply C inverse D inverse on both sides, right? And then you commute it. Okay, yeah, also work. Okay, so this two line works because the lemma work. Okay, can or not? There are few ways to prove, not just this way by Larry. As long as you are using axiom, okay, using the right operation, then you can prove it. Okay, not just one way to prove it. Try write your own proof. Okay. All right. Next, 10. How to prove 10? 10 is what? A over C plus B over D equals to, you need to make your denominator the same first. So why you need to make your denominator the same? You get that. Okay, so how to do it? Okay, so start from left hand side. Left hand side, okay, let's start from A over C plus B over D. So you use definition, is it? Rewrite the fraction into A C inverse and B D inverse, and then what next? Okay. You mean like this? Okay, and then yeah. Inverse plus BD inverse times CD inverse. Okay, good. And then you want to do distribute again. Okay, distribute. How to distribute? So you move all the inverse to the left hand side. Right. Okay, and then you use distributivity. Okay, use distributivity times C inverse D inverse. But just now we already proven that C inverse D inverse is just CD inverse. And which is AD plus BC over CD. Okay, so we are like producing one extra one there. Okay, does it make sense? Okay, so please go back and write down every step what axiom we have used. Okay, what theorem has to be true. Okay, so these are just results from field axiom. Okay, these are results from field axiom. So next, we're going to introduce order axiom. Okay, so we want to know which one is greater than what is greater than what. Okay. So order axiom, there are 5 of them. And there are 5 of them. There are 5 of them. So trichotomy. This is trichotomy. Oh, actually, do we have equality here? Actually, we don't really have equalities here. We don't have a transitivity there. So it's better we don't use that property to prove the lemma. We don't quite have equivalence relation on equality. So where's my lemma? Where's the lemma? Yeah. So maybe we can't quite use, let me comment here. Can't Right. Use transitivity of equality. Did we have this? I think we didn't define, right? We need to define it. For field itself, right? At least for the field itself, we don't have that. Do we have that? We have that. Let me see. Then yeah, the equal sign we use is the equivalence relation. I think we have. Huh? Yeah. Yeah, that's my problem. I think not quite. Okay, let me. So, maybe they hide it inside the axiom. So let me list down what is the order axiom, right? So first order axiom is trichotomy. So trichotomy, tri means three things. So what are the three things? So two number, there are three possibility. Okay. Given two number, there are three possibility. One, A is less than B, or A is equal to B, or A is greater than B. Okay. Three possibility, right? Two number. Either they are same, they are different. So how are they different? One is smaller than the other. The other is order preserving. Okay, so what do I mean by order preserving here? So A less than or equal to B implies that A plus C less than or equal to B plus C for any C. Okay, for all of C. Okay, if A and B, A is less than or equal to B, then we know that A plus C less than or equal to B plus C. Okay. Mind you here, this less than or equal or greater, right? Not necessarily the greater or less than in your mind, like whatever you know before. As long as they satisfy this property, they are less than equal or greater. Okay, make sense? We define by property, not defined by what you know before. And A less than B and C greater than 0 implies that AC less than or equal to BC. So if you multiply by positive, okay, in this positive meaning greater than equal to 0, but I don't know what is greater or equal to 0 means for now. Then it preserves the order. Okay. Positive, and for addition, any number, addition by any number will preserve the order. But only positive number can preserve the order in multiplication. Okay, on both sides. And then, I think we have it in the order axiom. So reflexivity says what? A has to be always less than or equal to A. Okay. A has to be always less than or equal to A. And anti-symmetric is if A less than or equal to B and B less than or equal to A implies that there's only one such thing. Okay, there's only one such thing can do it. Okay. Then imply A equals to B. The other one is transitivity. Okay, I think this is what Larry need just now. A less than or equal to B and B less than or equal to C implies that A less than or equal to C. Okay, so the order here is like we are defining less than equal. Equal and greater. Okay. Okay, that makes sense. Okay. So maybe the proof of lemma just now trying to avoid using transitivity first. Okay. Okay, so what's the good use of this? So the claim here is like this. Whatever greater you define, right? One have to be greater than 0. Okay. But in your normal sense, you will think that one thing is more than nothing, right? Okay. But this one is purely from structure. From structure, why one have to be greater than 0? Okay. Anyone want to try or not? So you are in the mathematics degree, or you should do something like this. Prove that 1 greater than 0. Now, why is it 1 equals 0? So there are three possibilities, right? Either 1 greater than 0, either 1 equal to 0, or 1 less than 0. Okay? But let's suppose we know that 1 is not 0. Okay? These two things is not the same. And we already know that these two things is not the same. I cannot suppose that I just said not that. We already know that it is not 0. Okay? Not that 1 is not 0. So either 1 is greater than 0 or 1 is less than 0. Okay? If 1 is greater than 0, then we are done. So now suppose for contradiction, 1 is less than 0, or 0 is greater than 1. Okay. So what can we do? Can we draw any contradiction or not? Then plus 1. You want plus 1 to both sides? Can, why not? But what does it do? So let's say we add plus 1 to both sides. 2 less than 1. What's wrong with that? Okay, maybe I do one trick. So I take 0, multiply on both sides. But just now, order axiom says what? If I take a non-negative value, multiply on the order, what do I get? I preserve the order. Okay. But 0 should be equal to 0. Zero should be equal to 0, right? Trichotomy said there's only three possible cases, either less than, either equal, either or greater. But we know that it's equal, so it cannot be greater or less than. Yeah.
Exactly one of the following.
Exactly. Yeah, exactly. Yeah, exactly. Yes, exactly. Correct. Exactly. Yep. Yes, exactly. Okay. 0 equals 0. Okay. So there's a contradiction.
Bigger than 0. You have both 0 from both sides.
Also wrong. Okay, so how? Does it make sense or not? Yeah, you are true. Wait, so let me think. Yeah. Yeah. Yeah, I think you are true. So how? So how? Two contradiction. No. 0 should exist. So what's wrong? What's wrong with here? What's wrong? No, right. Because this is what allowed by this order preserving thing. If A less than or equal to B and C greater than or equal to 0, then we have AC less than or equal to B. So what happened?
Less than or equal to. Just working with strictly.
Yeah, we're only working with strict equalities here. Okay, so how? So how? Can we play tricks again? Uh-huh. Divide 0? No, you can't divide by 0, right? So what can we do? Hmm? I'll do something like this. Try thinking about 2 or 3 minutes how to do. What contradiction you can get. Any contradiction you can get. Yeah, well, yeah. Contradiction you can get. Not just multiply 0 on both sides. All right, because we are in the strict case. So how we can, right? We can multiply by 0 on the both sides, but why the other case would be wrong as well? Be wrong as well. Okay, so how? No idea. Yeah. Let's try last try before we break. Huh? Huh?
Zero is
Both sides, and then we get 0 is less than minus 1, and then
and -1 is greater than
35 is greater than 0, so we can multiply -1 to both sides. No, wait. So what are you trying to do? Why can you multiply -1 to both sides?
because -1 is greater than 0.
Wait, so how? What? Why minus? Oh, okay, yeah. Okay, so we have this result here. Okay, and then, okay, so let's put this in. So, not that. It back here. Not that this is true. Okay, and then, so, multiply, okay, by order preserving. So you're trying to use by order preserving. And -1 to both sides. Like this. Is this what you want to get? Hmm?
Multiply -0 less than -1.
Sure, less than minus. You mean, oh, okay. So you mean this implies that you get -1 less than -1 times -1, like this, and then you get 0 less than 1. Is this what you say? No, it shouldn't fit right because this is using the order preserving property. But does this make sense or not? Yeah.
we are still one less than get 0.
Yeah. This is I know what's the contradiction you're trying to get, but I was trying to see whether this makes sense or not. Yeah, you. Ah, a square is bigger than 0. For OA. For OA non-zero, is it? A square equals 0, and then so what are you trying to do? Then okay.
Minus B is smaller when you go minus A. Yeah,
Minus B is smaller or equal to minus A. And then
you use the here's a theorem like A smaller than B and
uh-huh.
0 smaller than C. You can draw AC smaller than BC, right?
There's another thing you need to prove, is it? You mean this one? You mean this one? Okay.
Bigger than 0. E bigger than 0. AB must be bigger than 0.
Okay. Okay, so A equals A. B equal to 0.
Yeah.
And then
AB must be
A.
Yeah.
And then
and then
what?
someone one thing is like proof A squared is bigger or equal to 0. Bigger, very bigger.
So this implies that A squared is equal to 0. Together equals 0. Sure. And then
A smaller than B and B smaller than A, then you can draw A equal to B. And this is theorem of Einstein. So you can divide it into two situations. One is A smaller than B. No, one is 0 smaller than A. One when A is bigger than 0. So from the theorem of AB bigger than 0, you can draw A times B bigger than 0.
Okay.
So A squared is bigger than 0.
And then so what does this tell me about 1 greater than 0? Sure. But you haven't proved that 1 greater than 0.
We put it into situation like 1. The 1 is A small. 1 is A bigger than 0.
What do you mean? No, you cannot suppose what you want to prove.
The first one bigger than A bigger than 0.
Second
situation is A smaller than 0. And when A bigger than 0 from the theorem, when A smaller than B, 0 smaller than C, AC smaller than B.
Okay.
Yeah.
So try and write it down and then send it to me. Okay, then we will prove again this A greater than 0 in next class. Okay. If you want to try, you try and then send it to me, and then we will prove again why 1 greater than 0. Okay. Yeah, because we don't have enough time. Okay. Yeah, try write it down and then send it to me. Yeah, what's your argument? Okay, then we will prove again in the next class why 1 greater than 0. Okay. Okay. Okay, so let's see you on. I try to book next week replacement class. I'll let you know the classroom. Okay, Monday. And then not before. I think we need to go out. We need to go out. Yeah.
等一下，to go out quickly，想看的。